Mute everybody. Well, everybody should mute themselves and then ready to go.
Great, thanks. So welcome everyone to this edition of the Midwest Computability Seminar. Very happy to have Cristóbal Rojas from the Universidad Católica de Chile here. We'll be talking about computability of harmonic measures.
Thank you, Dennis. Thank you very much. Thank you for the invitation. Right, so this is a work that, well, we've been doing for some time, and the latest results are in collaboration with Ilya Binder, Adi Glucksam, and Michael Jampowski. This is my plan. I'll introduce the relevant objects I will be talking about, the Dirichlet problem and its connection to the harmonic measure. I'll recall the notions we'll need about computability of sets and functions. And I present the main results, and I'll try to give ideas of the proof at the end. Okay, so the Dirichlet problem is, well, a very well-known problem in which we have a domain, a region of Euclidean space, which in our case is going to be a bounded connected open set. So it doesn't need to be simply connected, so it can have holes. And the problem consists of, well, we're given a function defined on the boundary of the set that determines the boundary condition, which must be continuous, and we have to find a function UF, which is defined on the closure of our domain, which is continuous on this closure, harmonic inside the domain. So this means that the Laplacian of the function is 0. And it must equal the boundary condition at the boundary. So, well, this is a problem that appears in many different places. Well, here is an example. So the domain here is an annulus. The inner circle has radius 2, the outer circle has radius 4. And the boundary condition is 0 at the inner circle. And at the outer circle is this sine function, which has been amplified by 4, and the frequency is a bit faster than, well, this frequency. So it makes 5 terms, and you can see in this picture in the boundary how it looks. And then, well, here we also see the solution. And in the interpretation of the heat equation, we can think of this as F being some temperature imposed and fixed at the boundary, which then spreads inwards the set. And so inside the set, each point has a temperature that varies and eventually stabilizes. And at the equilibrium, the temperature is given by the solution. Okay. So there is a way of solving the Dirichlet problem that has to do with Brownian motion and harmonic measure. So I'll introduce harmonic measure now. So for the same kind of domain, if we have a point, we fixed a point inside a reference point, and let in this case T starting at X be a Brownian motion that actually will start at X, then the harmonic measure is a measure defined on the boundary of the set, which depends on the point where we started the Brownian motion, and gives to a given subset of the boundary. The value is the probability that the Brownian motion first exits the domain through this set here. So I'll make a picture. I'll make several pictures during the talk. So this is for harmonic measure. And so the idea is that if we have some domain, omega, and let's say a given point inside x0, and we pick, for instance, a subset of the domain here, S, then the probability, the harmonic measure of S, so the probability given by the harmonic measure to S is what we mentioned in Brownian motion, and well, is the probability that exists there. So actually, if we can sample Brownian motion, we can throw many of them and count how many of them exit through S, and then can actually approximate the probability by this sample. So for example, if omega is simply connected, like the one I draw, we have the Riemann mapping theorem that tells us that there exists a unique conformal mapping sending the unit disk to this domain omega, which actually sends 0 to the marked point X, and has satisfied this normalization condition, the derivative being positive there. And then using, well, it happens that this function can actually be extended to the closure of the unit disk. And then in that case, the harmonic measure of omega started at X coincides with actually the push forward of the Lebesgue measure in the unit disk when we send it to omega using this function. So omega harmonic measure in this case is defined by like this. So is the Lebesgue measure of the preimage of the set by this function. So for example, here in my picture here, if I draw the unit disk and 0, so that's get maps my phi to x naught, and then S will be something, I mean, this could be something like the preimage of S, and then we can compute harmonic measure just by looking at the Lebesgue measure there. Okay, well, this is the case, this is the simply connected case, the case which is most well known. Okay, so, right. So it is easy, well, to see that if I modify our domain omega by adding, for example, but not adding, actually by removing points of the set to, for example, one point, a few points, I don't know. Then, okay, well, this is not simply connected anymore, but what I want to point out is that by removing a few points, since the Brownian motion doesn't see actually those points, removing these points from the set, so adding them to the boundary, does not change the harmonic measure. And in order to get a connection between harmonic measure and the Dirichlet problem, we cannot allow this dust to sit there. So that is why there is this notion of regular points. So a point in the boundary is called regular if for every natural number, which here stands for precision 2 to the minus n, there is a distance such that if I pick a point which is close to z, closer than epsilon, then for sure we will exit the domain near x, well, not for sure, but with very high probability. Okay, so we are going to work with regular domains, so domains in which no dust is allowed. Okay, so with this setting, if we have a regular domain, then the connection between harmonic measure and the Dirichlet problem is given by a theorem of Kakutani, which says that if we have a continuous function on the boundary and define an the function UF at a given point inside as the average value of the boundary condition with respect to harmonic measure at that point, then this function that we get is actually harmonic inside and converges to F at the boundary. So this is actually a solution for the Dirichlet problem. And well, the extended function, including the boundary. And so, yeah, well, so in our picture, if we have a value at the boundary and I don't know, we sample several, we want to know the solution at this point is 0. So we should have several samples of the Brownian motion. And each time we hit the boundary, we look at the value of the boundary condition there, and we average all of them. And that gives, the value of the solution at x0, or an approximation if we're average like this of finitely many samples. Okay, so those this is the problem. And the question that we look at are the following. So given for a regular domain, so we want to know what information about the domain that we need in order to actually compute this harmonic measure. And conversely, if we are able somehow to sample from the harmonic measure, what can we learn about the domain? These are the two questions that we have studied. So in order to state the results, I'll recall the definitions that are involved. So in terms of sets, I would call lower computable open sets for which we can compute the sequence of balls that exhaust the set as usual. Closed set, we call them upper computable when their complement is a lower computable open set. We call them lower computable when we can enumerate all the rational balls that intersect the boundary, which is equivalent of being able to enumerate a dense set of computable points inside. And well, incomputable if both things are satisfied. Okay. For functions, we have three versions of computability of functions. The first one is only at a given point. So we say that the value of the function at point x0 is computable relative to x0 if there is an algorithm that actually computes the value if provided with x0 as an oracle. But we don't claim anything else about what the algorithm does for all the points, only at this point. A function, we call it piecewise computable if for each point in the domain, the value of the function is computable relative to x. But we may need different algorithms depending on the point. And computable if it is piecewise computable with only one piece. So the usual notion of computable function. So the value is computable in this case relative to x uniformly. Okay. Right. And for the measures, the definition of a computable probability measure is as follows. We need to be able to compute the integrals of computable functions uniformly, in the sense that if we have any list of computable functions which is uniformly computable, then we can uniformly also compute their integrals with respect to this measure. And well, for instance, Lebesgue measure, any measure with a computable density is computable with this definition. And also, it's easy to see that if we have a computable measure, then it's a closed set, which is actually lower computable according to our definition. So we can enumerate balls with positive measure, essentially. Okay, so the first result is the following. We assume that we are able to sample harmonic measure at one point and nothing else, only that. So there is a regular domain, and the assumption is that the harmonic measure at the given point is computable relative to this point. Well, this is redundant because we are taking a computable point. So, okay, and so what can we do? Can we sample at other points? Can we say something about the set? What is this good for? Okay, and so the first result is that if this happens, then harmonic measure is actually computable relative to X for all other points in the domain. Note that here there is no computability assumptions whatsoever about omega. But it might happen actually that the computability is not uniform. So we will see that an example that requires different algorithms. However, if we assume, moreover, that the set itself is lower computable, then this phenomenon cannot happen, and harmonic measure must be uniformly computable. So a single algorithm. And so there is a natural question that we cannot answer, which is whether every domain with a uniformly computable harmonic measure is actually lower computable. So we don't know of any example that says that this thing cannot happen. I mean, that we do not have the converse implication. Okay. So at the end, as I said, at the end, I will give ideas of all these things. Okay, so the connection, when we connect this to the Dirichlet problem, we get a kind of strange solution or situation in which, so there is a regular domain and a computable boundary condition F, and such that the unique solution of the Dirichlet problem can be computed. I mean, the values can all be computed relative to X, but the function is not computable function, regardless that this not only continuous, but even harmonic. Okay, so this is a consequence of that result. So the next question is, okay, what happens if we know the domain very well? Can we compute the measure? Well, this theorem says that only knowing topological data about the domain is not enough. So there are regular domains for which, well, they are as much computable as you may want. But regardless of that, harmonic measure is not computable actually for any point. So there is more information about the domain that is needed in order to compute a harmonic measure. And one such additional sufficient information, so this is the geometric condition. Well, it's maybe not very surprising, it's just the computable version of regularity. So if we have a function that we can compute a function which actually tell us how close we need to be of the boundary in order to exit nearby with very high probability, then with this, well, in the case in which we know the set, so we're assuming it is computable with computable boundary, then computing the harmonic measure at some point at all points is equivalent to the set actually having this property of being computably regular. And actually, if we do not assume that the set is computable, only assume it is regular, but we know that we assume that it's actually computably regular, Then there is another theorem, I didn't write it here, which actually says that in that case, being computable at some point is equivalent to being uniformly computable at all points. And in that case, that implies that the set must be lower computable. So, well, this is the situation. Okay, yeah, so those are the results that I wanted to present. So these are the statements, and now I'm going to give ideas of the proofs. So I'll start with this one. Okay, so we have these three parts. So I'm going to show first the idea of how to compute the harmonic measure at every point. If we only know how to compute it at one point without knowing everything else about the set. So the first thing that we need to know, or that we use, is a kind of lemma, which is that if the sets are nice, for instance, computable polygons, they always have uniformly computable harmonic measures. So, okay. So if our set is a polygon like this, and it doesn't matter where our point is, we can always compute harmonic measure at that point. So now, knowing that, having that in mind, okay, let's assume that we know how to compute the harmonic measure of omega, the unknown domain. Okay, so okay, in some sense, we have x0 given, and we can kind of start growing in motion, and somehow we know where it exits, or we can see that it exists somewhere with some probability. For example, first there, I don't know. We can have like parts of our domain by sampling, by using this measure. And we take a different point, y, and now we want to know what is the probability of exiting, but starting at y, right? But we don't know anything of the domain except the fact that, well, we see it with some probability, some parts. Okay, so what do we know? What do we do? So the idea is to use two things. The first one is use the fact that polygons, so we use that polygons are dense in the collection of all domains. In the sense that that for any domain, there is a sequence of polygons actually that convert to that domain, in the sense that the corresponding harmonic measures at our given point with respect to these polygons converge weakly. Pick a star, I don't know, with respect to the weak topology of measures to the measures of our domain. Okay, this has to be proven, but it's true. And now what we do is, the idea is to, well, enumerate all polygons, compute their harmonic measures. And given that we know this measure, so this is if we want a computable point in the space of measures, then we can select polygons for which harmonic measure is close to this one, and actually then build a sequence of polygonal domains that satisfy this with actually a rate of convergence that we can choose as fast as we want. So what do we do with that? Okay, so then we need some, in order to achieve our goal, which is to compute the measure of omega, but with respect to other point y, we need some non-uniform data, which is, okay, we have x0, we are given y, but we need to find first polygon to start with, which has to contain x0 and y. So if x0 is there and y is there, we need to be given or to guess one first polygon in order to then start enumerating some more polygons. And I don't know, that somehow we know by computing their measures that they approach the measure of omega at x0. So the actual domain, we still don't know it. And we don't know the topological connection of our polygons to the domain. All that we know is that the measures of the polygons Pn, so this is Pn minus 1. As I said, they convert to our given measure. And it is important that we can choose the rate here. Okay. So once we have done that, well, in order to work here, we need actually the polygons that we construct to be increased. And then, well, you might guess, for each polygon that we have constructed, because they are very nice domains, we can not only compute their harmonic measure with respect to x0, but also with respect to y. And now the deal is how to control the convergence. So now we can compute the measure of this polygon with respect to y, and well, we use that this converges to the measure we are looking for, but we have to make the rate here computable. And for that, we use Harmonic inequality. So Harmonic inequality gives a connection between the two harmonic measures up to a multiplicative constant. Harmonic and the fact that we can choose this rate to be as good as we want, then, well, we pick it in such a way that when applying Harmonic inequality, here we get some computable rate that we ask for. Okay, that's how do we prove the first part of this theorem. Actually, the third part, which says that if we assume the domain itself to be lower computable, then the computability of the harmonic measure becomes uniform, can be seen already here, because in that case, we do not need this non-uniform information anymore. If we know how to enumerate the domain omega, well, then all this construction can be done uniformly. And that's why the third point is true. And for the second point, we have to build an example, a counterexample. So the non-uniform example, how does it work? So, okay, there's also an idea here which is behind the construction. So we assume, okay, there is some domain again, omega, and we have some point x0, and let's suppose that we are looking probability that Brownian motion exits that way. So I don't know, it does something like this. Imagine that this one, we got lucky and it went through S. Okay, and so, okay, this S has a certain probability. Now I'm going to modify the domain and I'm going to kind of shield the S on all the parts of the boundary with it. So I'm going to remove something of the domain in order to make the Brownian motion very likely to actually hit here, right? So at the moment that I remove that from the domain, so I add that to the boundary, the probability of S will get much more smaller. Now it's much more harder to get to S. So, well, this is the idea. Now I'm going to build, we are going, so okay, let's do it. Okay, so using this, we can construct, for example, inside a circle, we are going to mark point x0, x1, x2, and so on, one for each machine. So we enumerate machines. And okay, and for one of these mark point corresponding to the end machine, so we either add some shield with a certain radius, which is going to be well, smaller for machines that take longer to halt. So this is going to be the halting time of machine MN. So this is in the case that the machine MN actually halts. And we are going to do nothing. So there is just the mark point, which is not, that belongs to the set and to the domain. If the machine doesn't halt. So longer it takes, smaller are these disk or shields. So that means that we will have some of this shield and some others won't be. I don't know. And now, well, you can see that what are the properties of this domain? Well, first of all, if you pick a big chunk of the boundary and ask for its harmonic measure, starting at any of these mark points, then, well, you see, right, the measure will be big if we are here, for instance, which corresponds to a mark point for a machine that doesn't hold, or it will be much smaller if we started from a point which has been shielded because the corresponding machine did hold. So if we were able to compute harmonic measure uniformly at all points, well, we could solve halting problems. So harmonic measure is not uniformly computed. On the other hand, if we take now a different point, say y here, harmonic, well, we want the harmonic measure to be actually computable relative to y. And well, because of the theorem, then it will be relative to all other points. So showing it for just one point is enough. And okay, and this works as follows. So as always, we simulate all machines for long enough. And if we want to compute harmonic measures, say at position epsilon, then we run the machines for a time which is long enough such that all the shields that may appear but that have not appeared yet are very small, in the sense that their harmonic measures of all of them is less than, well, this thing, divided by 100. It's very small relative to epsilon. And then, well, the remaining of the set now is a nice set. And for that part, we can compute harmonic measure. So, well, yeah, this gives the complete picture of how this construction works. Okay. So, well, this is just, there is nothing to show here. This is just, we need only to pick one particular function, and this is a direct consequence. And, right, so, and then there is this other example, which is a set that has to be computable, but now we want the harmonic measure to be non-computable at every point. Okay, so how this thing works. Okay, so this is example, let me say example 2, a non-computable harmonic measure. So the picture here is the following. So we we start with a, let me try to do it more like a half of a circle. And in the top part of the circle, we are going to add this, these bumps, smaller and smaller. And okay, and now let me, for instance, pick a point here. And okay, so Brownian motion will start from there and will hit these bumps with certain probability. And that is what we have to control to produce this example. So the way of doing this, so this is too small. Make it a little bigger. So the way we are going to do this is by adding also a barrier, but okay, so it can be of two sorts: a hard barrier or a dash, like or a dotted barrier. But in both cases, we are going to leave some space there, fixed space, always the same, well, proportionally the same, in order to make sure that Brownian motion can actually always get there. Otherwise, this would not be part of the domain. And okay, so some of them will be dots, some of them will be hard. And how do we decide that? Well, once again, this corresponds, we have each bump will be associated to a given machine. And in one case, we will make a solid barrier when the machine doesn't halt. And when the machine halts, we will make a dotted barrier. This is when the machine halts. And the idea, well, I'm not going to write precisely how it's constructed, but it is, we feel more for longer times of halting, for longer halting times. Feel more means with well, with more little dashes, right? In a way that for Brownian motion will always be easy to go through. But topologically, this barrier here converges to the solid barrier. Those are the conditions. So what happens when we do this? Well, first of all, if, well, the first part is simple. If we were able to compute harmonic measures starting anywhere, doesn't matter, then once again, one can compute a priori how large will the measure of one of these bumps need to be in order to know that actually the barrier was open. And so by computing the harmonic measure, we can decide whether the barrier is open or closed, and that cannot happen. So in this case, harmonic measure is not going to be computable with respect to any point. And the set itself is quite well computable because once again, we simulate all the machines and get track of those that halt. And for those, well, we actually draw the open barrier as it has to be and leave the others. Yeah? So for instance, this one, or I don't know, this one, actually might correspond to a machine that actually doesn't halt. But if we truncate the process at some time and we draw this, then that's actually an approximation of the final set, the Hausdorff distance, for instance, that we can compute. Yeah. So this set is completely computable, but their harmonic measures are not. And perhaps one more remark here, the condition of computable regularity, which here is not satisfied, implies actually that, or actually forbid us to make this trick because it forces us. It says that if we are near the boundary, so there is a function that tells us how near we have to be from the boundary in order to make sure that we will exit the set near that point. And this is exactly what we cannot do here. And yeah, so you can get an idea of why computable regularity excludes all these examples. And I think that is all I wanted to explain. So let me go to this slide.
Thank you very much. Are there questions?
I have a question.
Go for it.
Okay. In the second example, why is the boundary computable?
In the second example, well, yeah, so yes. Yeah, okay, so, well, as I said, when you let the machines run and if you want to compute a Hausdorff approximation of the final set, you say at precision epsilon, then you can compute how long you need to look at the machines, such that if you wait up to that point and then stop the construction and do for the ones that have stopped, you draw what it must. In the others ones, you, for example, here, or if this one doesn't hold, but you don't know yet, instead of this, you will draw a dotted line, which will approach this one in Hausdorff dimension. So that's how or why the set is computable, the boundary.
Okay.
Thanks.
Oh, sorry. Sorry, I changed it because when I put the blackboard, I cannot see it. I don't know why.
Got it. Are there other questions? Anything else from the room there? If not, let's, yep. So
We're good.
okay, great. If in that case, let's thank Cristóbal again.
My pleasure. Thank you.